In this talk, I would like to present work done in collaboration of the Flowers team at INRIA and Enstar Paritech with Bielefeld University. I will focus on presenting a new experimental setup we developed for studying the co-construction of interaction protocols in collaborative tasks with humans. And I will also present the first results of a pilot study we conducted with this setup. The overall general aim of this research is flexible communication between humans and robots. For robots to be able to learn from human instructions and for efficient human-robot collaboration. Some of the things robots need to be capable of are, for example, understanding unknown feedback or guidance signals, making sense of what they refer to depending on their timing and context, and agreeing with the human partner on how to organize the interaction into roles and turns. To achieve this, we first aim to understand the interactional flexibility of humans, how they align and how they create common ground. Human communication is very complex, so we need an experimental setup with constraints that lower interactional complexity but still allow analyzing communication. And we want to inform human-robot interaction on the long run. Thus, the setup should incorporate certain characteristics of human-robot interaction. In this setup, communication should be asymmetric, as humans and robots do not perceive the world in the same way. Additionally, human and robot might not have established a common protocol of interaction, and also humans might not understand how exactly their signals are perceived by the robot. To investigate the processes humans use to negotiate a protocol of interaction when they do not already share one, we came up with the COCO game, where COCO stands for co-construction, which is played by two participants. In the game, they have to complete a joint construction task assuming asymmetric roles and communicating over restricted channels. Participants have to build a structure out of building blocks together. They assume the role of a builder, who has the building blocks, and the role of an architect who knows what to build. But communication is not face-to-face. That would be too easy, but it is restricted. So the setup looks as follows. The builder and the architect sit in separate rooms. They do not see or hear each other. The builder has the building blocks and the architect has an image of the target structure and thus knows what to build. Each participant has a screen in his or her room. The workspace of the builder is recorded via a webcam and shown on the architect's screen. In the other direction, the architect has a box with 10 buttons with which he or she can communicate with the builder. When the buttons are pushed, they make symbols appear on the builder's screen. The symbols are neutral, and neither their shape nor color are related to the task. Each symbol has a fixed position for one round, but where the buttons are on the architect's box does not correspond to where the symbols appear on the builder screen. The players do not know this mapping. And if the architect would push all of the buttons at once, then it could look like this on the builder screen. The game ends when the builder decides that he or she has built the target structure correctly. And all of what I just told you about the setup we also told participants of the study before the game. Additionally, we told the builders they should not use conventional gestures, as this would also be seen by the architect. In the pilot, participants spoke aloud about the meanings associated to the symbols and buttons. For the pilot study, 11 pairs of participants played the game. 7 of these pairs played the game for a second round, for which they switched roles. So the architect in the first round was the builder in the second round and vice versa. We excluded one round because the architect did not stick to the target image and made up his own construction. Thus, for the analysis, we considered a total of 17 rounds. The game sounds rather difficult in theory, and now I want to show you a video clip showing an excerpt from the beginning of a round. You're more than welcome to try to figure out what the architect is trying to tell the builder. It still seems difficult, if not to say hopeless. But in the end of the same round, communication is rather structured and most participant pairs do succeed. So even though most participants before the game thought that they would never be able to succeed, 13 of the 17 rounds were successful and only 4 failed. A round took 18 minutes on average, where the fastest diet only took 7 minutes to succeed, and the maximum duration at which we stopped the game was 45 minutes. Here you see a visualization of the whole round I showed you in the video clips. It contains information from architect and builder plotted against time. On top, you see the architect's button presses and their intended meanings. Below, you see what the builder thought these meant. We see that in the first 4 minutes, so here, the architect pushes many different buttons with different meanings which are not aligned with the builder's interpretation. Button 4, for example, means under for the architect. But this is not what the builder understands. For her, the symbol appearing with button 4 refers to the color yellow. The architect seems to notice that something is going wrong and at 4 minutes pushes all buttons to signal a reset of communication. And from this point, he only uses a simple yes and no strategy. On the builder side, this reset signal is followed by a long pause in actions, which actually hints at a direct confusion. You can see that here on the bottom where we have a progress graph showing how many correct and incorrect blocks and connections between blocks are in the builder's workspace. Correct in gray and green and incorrect in red and black. It is only at 12 minutes that the builder and the architect fully understand each other and they can start building. We observe a phase of confusion and negotiation at the beginning of the interactions, and after that a completion phase in which signal meanings have been constituted. All the way at the end, the architect pushes again all of the buttons, but this time not to signal a reset in communication, but to signal that the target structure has been successfully built, and the builder understands this signal. For all 17 rounds, we looked at the types of meanings participants attributed to buttons and symbols. All participants considered positive and negative feedback. Also, the end signal was often used. We also find a reset signal, guidance signals, which are instructions on what to do, such as change, invert, continue, references to color and size of blocks, location signals, such as right, left, above, and below, or signals referring to a group of blocks. Then we wanted to know about the amount of shared understanding between players in a round, and if it was more in successful than in unsuccessful rounds. For successful rounds, the average number of signals understood, that is those where architect and builder agree on a common meaning, is 3.6. Interestingly, for failed rounds, this number drops to 1.3, with a larger amount of signals for which architect and builder reported different meanings, we termed these misinterpreted, and signals which the architect but not the builder mentioned, we termed them ignored. Next, we were interested in what meanings exactly most pairs agreed on, and these were positive feedback, negative feedback, and occasionally reset when needed. Humans seem to solve such restricted asymmetric interaction problems by projecting the interaction into different common frames of interaction and selecting the one that is most coherent with the history of interaction. The feedback frame seems to be the most commonly thought about and the easiest to understand in the context of our experiment. The last analyses I presented so far focused on the meanings of buttons and symbols, that is, on the architect's actions, and the next slides are now about the builder's actions. We identified two main builder strategies, which I will show on the following slides. But some builders also did not embark on any apparent strategy. The most common strategy for builders was to find one correct block at a time, and then to subsequently find the correct position to join it with the rest of the structure. Builders in 12 of the 17 rounds pursued the same strategy, and only one of these failed. And it failed because there was a mistake of one block being in a wrong position in the early construction, which was not corrected by the architect right away. The architect waited until the end to correct it by introducing a new signal, but this signal was interpreted by the builder as being an end signal. The other strategy was to one at a time find all blocks belonging to the target structure by dividing the blocks into two groups. Then correct blocks were joined in the next step. This strategy was pursued by two builders in two successful rounds. 3 builders presented multiple, sometimes even joined blocks at a time throughout the game. Their rounds all failed, with an end structure which was nowhere near the target structure. Thus, the way the builders propose next steps and ask for information from the architect seems to be important for the success of the game. Builders seem to build frames and create slots for the architect's input. These frames are then the context in which the signals are interpreted. If we want to replace the builder by a robot, not pre-programmed, on how to understand human communication and without a specific pre-programmed rigid interaction protocol, then we should equip the robot with a set of common interaction frames on which it can rely to find the one that is coherent with the interaction history. And a mechanism of proposition, as we see in the builders, providing frames with slots for the architect to give information in a learning robot, could be a means to elicit appropriate signals from a human tutor in human-robot interaction. In the field of robotics, there's recent work on this topic. For example, the following work by Grisou and Cederborg develop algorithms that allow a robot to learn to interpret the meanings of social signals and a task at the same time. Thank you.